Welcome to the Calsoft podcast series. This is your host Mark Rodrigues, and today I have with us Imran Khan, Architect Storage Solutions at Calsoft. Imran spearheads a team that works on file systems and storage solutions. So let's jump right into the topic we have lined up for today, which is logistics for change block tracking. Welcome Imran.
Thanks, Mark. It's great to be here.
We're glad to have you here too, Imran. So quickly, why don't you walk us through what exactly is change block tracking?
Okay. So change block tracking or change tracking or CBT, it's nothing but making a record or a journal of which blocks of a storage object were changed by I/O. When you do I/O, you touch the blocks of a storage object and we need to record which blocks have changed. A storage object is any logically contiguous space used for storage of data.
Okay.
For examples, you have files, you have raw block devices, you have LVMs, partitions, even virtual devices like VMDKs or RAID devices. Now, you need to keep in mind that CBT does not keep track of what data was written. It only logs which areas of the object were written. So such tracking data can be used by various applications, primarily backup and restore and solutions, and others are out-of-band, dedupe, archival, etc. solutions. And usually, such tracking is performed to know what blocks have changed during a given time frame.
Okay. That's interesting. So here's a quick question. Don't backup applications use snapshot technologies? I mean, where does CBT have a play in all of this?
That's very true. So traditional backup applications, they rely on snapshot technologies to take backup. Now, snapshots are essentially point-in-time copies. You know that they are point-in-time copies of the storage object and make the backups consistent.
Okay.
However, it's very tedious to take backups of the entire object at every backup cycle. So what do? The answer is either use incremental or differential snapshots. Now, using incremental snapshots, one can know what has changed between two snapshots, right? Now, backup applications use this information to know what blocks of the object to backup.
Okay. Is there an example that you can elaborate this with?
Yes. Let me just give a small example.
Sure.
Now let's take an example of backup using traditional snapshots. Now here we assume a block device which is capable of snapshots. For example, let's just take a name. Let's say Dev SDA. Now at the first backup cycle, what we do is we take a snapshot of the device and we take a full backup using that snapshot. Now, at the next backup cycle, we take an incremental snapshot of the device. Now, this logic, snapshot logic, is already provided by the block driver. Now, what we do next is we calculate what has changed between the two snapshots and take the backup of only those areas. At the next backup cycle, which is maybe a few weeks later or maybe a day, we take another incremental snapshot of the device and then repeat the cycle. So what we can notice here is that the snapshots have to exist not just for the period of backup, but for over two backup cycles, or it may even require to exist for more than two backup cycles. Point number two, production I/O has always the need to go through this snapshot layer.
Right.
Meaning that if you have the snapshots in the I/O path, then every I/O that you do may translate into more than one or read or write based on what type of snapshot it is. Okay. Now, third point is that since these snapshots, they have to live for a longer time, and the size of the snapshots will keep growing as much as you do I/O to it. And when you really want to delete these snapshots, it will be very time consuming and tedious because these snapshots are so large that it takes time to manage all the data in the snapshot areas. The effect of these points 2 and 3 that I just said, they are multiplied when the backup interval is large. So let's imagine that your backup interval is a week, right? Now, in case of redirect on write snapshots, it would mean that you are merging the entire weeks of data from the data area onto the base device.
Okay. So could I encapsulate by saying that all of these points would degrade the performance of the production systems?
Very much so. And
Okay.
that is one of the problems that CBT is trying to solve.
Okay. So can you elaborate a little more on that?
Right. So change block tracking, as I mentioned, it keeps a continuous track of which block have changed between a given time interval. Now backup applications, since they used to rely on snapshots to know what has changed.
Right.
But CBT provides that information out of band to those guys, to the backup applications. Hence, these backup applications, they don't need to keep the snapshots alive after
Okay.
the backup is complete.
Okay. Moving a little technical now, what do you think is can you elaborate a little more on the flow of backup when CBT is in play?
Sure. To take a backup, one essentially needs to know what has changed between two snapshots.
Right.
Otherwise, you need to keep taking full backups every time.
Sure.
Now, for this to happen, as soon as the snapshot is taken, any new IOs that are attributed to the next snapshot.
Mm-hmm.
Meaning a new tracking instance has to be started atomically with the creation of the snapshot.
Mm-hmm.
Okay. However, changing or integrating with existing snapshot technologies is difficult and something that is really speaking not necessary. Okay. So this problem is easily solved by using two simultaneous tracking instances which overlap across the snapshot creation operation.
Sure.
So let's just take an example here, right? So what you do is you start this, for example, this is the timeline that is given here.
Right. Right.
You start from the left and go towards the right.
Sure.
Now what you do is you start tracking first whatever the object storage object is there. We start tracking, let's say the instance is T1 or 0.
Okay.
Then you take a snapshot of the device followed by a full backup. You always start with a full backup first.
Right.
And as soon as your backup is done, you delete the snapshot.
Mm-hmm.
Since you already have a tracking out of band in place.
Okay.
Now in the next backup cycle, which may be a day later, a month, a week, whatever, you start another tracking instance which is, let's say, TI1.
Sure.
Okay. Then you follow it up with another snapshot, S1. Now what you do is, after you have taken a snapshot, you stop the tracking instance T10, which you had started a week back.
A week ago, yes.
Right? Then what you do is, now the tracking instance T10 has all the changes that has happened to that storage object in that particular week.
Right.
So you use that T10 to take an incremental backup.
Right.
The backup just needs to know which blocks have changed, so it can just read that information and take the specific backup.
Okay. Okay.
Once your backup is complete, you do not need that particular snapshot anymore. So what you do is you delete it. So you can see that the snapshot only exists till the time that backup needs.
Okay.
And it does not need to live for anymore. And essentially there are no incremental snapshots. There is just one snapshot alive that you need for each backup.
Right.
Okay.
So I think this image helps put things into perspective. Could you maybe tell us a little more about the components that encompass CBT?
Right. I have been designing CBT for a couple of solutions.
Sure.
And in those particular solutions, what I see common is that there are two major components that are required for CBT. Right. The first one is basically the hook or the filter. Now, what I mean by hook is that it is something that allows you to take a peek at the I/O on the storage object.
Okay.
So whenever an application does I/O to that particular storage object, you need to know which blocks of the storage object it is touching. So the most important requirement for such a hook is that it has to be fast.
Sure.
Why? Because the problem that we are trying to solve by using CBT is to lessen the delay on the I/O in case of snapshots. Right? And the same needs to hold true here. This is actually easily solved if you have an intermediate fast cache that is available there for the hook to record all the tracking data. And this tracking data can be asynchronously written to persistent record later. Right? Also, the hook does not need to care whether the IO itself is successful or not. It is just taking a look at what potential blocks can be touched and recording them.
Right.
Okay. And the second component is the persistent record itself. Now, it's not necessary that you have this record on disk. It can be an in-memory record as well.
Okay.
Or it can be something like a map disk as well. But the format of this persistent record should be in such a way that it is easily consumable. Okay. Now, for example, you have various formats. You have a log structured format where the tracking data is just appended to the end of the record. However, it may result in more post-processing. For example, to know what has changed between a given time frame, you need to go through the entire log and try to figure out the areas.
Sure.
Okay. Now, VMware proudly uses such a structure because it uses a CTK file associated with the VM, right?
Okay.
Now, another format of a persistent record is a bitmap, in which every bit it represents a logical extent of the storage object. Now, this bit is set if the logical extent is partially or fully written. It doesn't matter whether if a logical extent is, let's say, 256 KB. Even if you write 4 KB of that particular extent, we consider that block as written or touched.
Okay.
Okay. This essentially avoids having a large bitmap size. Okay. And multiple bitmaps can represent multiple tracking instances. So it's very relatively easy to consume.
Okay. So would it be safe to say that, operations like merging of bitmaps can be performed?
Yeah. Merging of bitmaps is another operation that can be easily performed. And it's rather difficult to do that on a log structured file system. So if you have one tracking instance represented by a bitmap and another tracking instance represented by another bitmap,
okay,
and you want to know what data was changed across both instances, you just need to merge the data.
Okay.
And you have you have the needed data there.
Okay. So Imran, you mentioned a little while ago that you've worked quite a bit on designing CBTs. What do you think are the most important things to keep in mind while doing that?
Right. So as I mentioned that one of the most important components of CBT was the hook, right, or the filter. And the problem that we are trying to solve is performance degradation in production IO. So the most important, I think, is that hook, it has to be fast enough not to degrade the IO performance. However, more important than that, it has to be sure to capture all the IO paths. I mean, you can never ever miss any tracking even one IO.
Okay.
Because if you miss even tracking one IO path to that particular block or device or storage object, the tracking data itself becomes inconsistent and it results in a corrupted backup.
Right.
And moreover, this corruption will only come to light during restore, which is much later in the time frame. I mean, you won't know while taking a backup you have taken a corrupted backup. It's only during restore you know that your data that you are restoring is inconsistent.
And we definitely don't want that happening.
Yeah, sure, man.
So can you play out some other scenarios that come into play with CBT?
Some scenarios, some key points or scenarios that come into mind are, for example, unique identification of a storage object. Basically, your backup application and your tracking filter or the tracking software, they have to be on consensus on how to identify a storage object.
Sure.
Right? And it is generally very easy. It's not that difficult. For example, you can use, if you are tracking files, file name itself becomes identifier. And if you are tracking SAN devices, then SCSI ID is one identifier. And if, for example, if you are tracking LVMs, then LVUUID or the LV unique identifier is one of those identifiers that you can use.
Okay.
Major minor numbers in Linux, they are not a good example because they tend to change sometimes when the system is rebooted. So you definitely don't want major and minor number to be used as unique identifiers. Another scenario is talking about reboot. reboot is one good scenario that you need to keep in mind.
Mm-hmm.
Sometimes what happens is a device is accessible at very early stage in the boot.
Mm-hmm.
And if you're tracking that device, and since one of our goals is not to miss any IOs, your tracking filter or hook, it needs to be in place before that.
Okay.
Similarly, during shutdown, no writes or IO should be missed. If you want to take a lazy approach, you can always say that if you are unable to capture and track all the IOs during shutdown and boot, you just take a full backup every time a machine reboots.
Okay.
And you start a new tracking instance for the cycle.
Sure.
Right. And another scenario, for example, is devices being renamed. Of course, if you are using the unique identifiers, you don't need those. You're not in so much of a trouble. But Linux also allows you to allows for the storage object to go offline and come back online as a separate device. So
Okay.
your CBT needs to know that a device that it was tracking is now coming up as a separate name.
Okay. Well, wonderful. That's very insightful. That is a wrap for us for today. Thanks for joining us for this podcast, Imran. This definitely wraps up information-packed podcast. And for our listeners, like always, in case of any questions or further clarification required, please write to us on smm@calsoftinc.com. I'll repeat that email address again. It's smm@calsoftinc.com. Thank you for your time and have a great day. And thank you once again, Imran.
Thanks, Mark. It was nice to be here.
Thanks so much, guys. Bye-bye.